The new microsurgical platform. This platform is not totally new for the one who were already here last year or here at the RAMSES, but we'll see the new developments. Thank you.
Thank you. Good afternoon, everybody. Good morning to the Americans, by the way. Yes, I'd like to update a bit about our progress we made with a new robotic platform that we have thought of in Holland. Last year we already introduced this platform, and this year I'd like to tell more about it. As last year we only had the system ready and tried it out for a couple of weeks. So today I'm going to talk a bit more about the test. Thanks to Jesse Selber, I can win some time on this because I think we've got the same vision on it. I'm from the Maastricht University Hospital, plastic surgery department, and we have a strong focus on reconstructive surgery, which today is a lot of reconstructive microsurgery using free flaps, which means transferring tissue from one side of the body to the other. And you need to reconnect these vessels, and they are small, and they get smaller and smaller. So we need precision, and we also think you need a robot for that. So when Da Vinci came out with the robot, everybody was keen on trying it. So was our unit. So we were the first to report a free flap for breast reconstruction, which we call deep flap. Take the skin and subcutaneous fat from the lower part of the abdomen, and you transfer it to the breast. And we used the Da Vinci those days, 2007, and we concluded this machine is not for microsurgery. It was too big, the instruments were too powerful, and we thought this is not the way to go. Let's try something else. So we started from scratch. We took our brain out of the console of the Da Vinci and started thinking again. And what we thought of concept of microsurgery is we think that every time you need a microscope to enhance your eyes, you should use something to enhance your hands. So we're looking at 20 times magnification with our eyes, and we still operate with some gloves on, and that's it. So that's our goal. So we don't need the telesurgery yet. It's nice if it's possible, but that's not what the code we want to crack. We also got our 3D vision. I think it's better to look at a good microscope, a modern microscope, than to look through this 3D camera of the Da Vinci nowadays. So we thought, let's focus on something that is small, that is attached to a good microscope, and that enhances our hand. So together with the Technical University of Eindhoven, we started from scratch and focused on precision of the hand and cost efficiency, and of course safety. So this was the idea, a ring on a microscope with 2 or 4 robotic arms in a master-slave situation. And on the right side you can see our first model that was made, and we presented it last year. So we started simple, pointing tasks and tracing tasks to see what this robot could do. So it was a needle holder. I should say the robotic platform is using the needle holders we're using with our hands as well, to save costs as well, and to focus on what we need to improve. So a small needle, and we needed to draw a line. A microsurgeon, a registrar, a plastic surgery, and a technician. And you had to stand still on every corner for 3 seconds. And if you see, obviously the robot is better in standing still. It's got thermal filtration, and because of the pixel in the camera, you see a little bit of error as well on the robot, but we think that's a measure of the camera. What you can see as well is this is going from itself. The experienced microsurgeon is doing better than the rest, but the robot is obviously better. And in the tracing task, you can see the same. The microsurgeon just wins from the machine, but the others don't. The robot is better. And what you can also see is that the robot has got a fairly constant performance in all levels of tested individuals. So after performing this, we started on microvessels, silicone, just as we saw. We used 2mm diameter vessels. We used 9/0 sutures and also 8 sutures. And what we measured was time and adverse events, quantitative outcome, and qualitative outcome. We checked the patency of the anastomosis, and we also filmed the anastomosis and reviewed it with the expert panel that was blinded. But we used the SAM score, so that was the basic score, and that's because we wanted to compare the hand with the robot. And the SAM score is good work, and it's really good work, but I think you can't compare the SAM score to the golden standard that is still open microsurgery by hand. So that's what we chose for the SAM score. It's already mentioned, it's the same score without the robotic part. And when we look at these anastomosis, so it's done by a microsurgeon, a registrar, and a student, and we wanted to see how that goes. Time to anastomosis took longer by a robot. But you can see after 10 anastomosis, the learning curve is really nice in the robotic field. The overall SAM score, also you can see the hand still wins from this robot, but the robot is getting there within 10 anastomosis. And one of these blocks is the indicative scale, which shows a conclusion of what skill level has been performed. And you can see that the robot is already there. So that looked promising. However, there were adverse events, and the time-consuming robot, you can see why that is. So we had some involuntary movement, a bit of robotic crash, which sounds a bit harsh. The robot didn't explode, but there was a software problem which needed a reset of the system. The majority of the problem was that it was out of range. So that has to do with setup and the device itself. So after performing that, we went on and we did a pilot study on microvascular anastomosis in rats. And we started using 6 rats, general anesthesia, and we started with abdominal aorta first. That was our goal, and see how the robot would perform. But because that went well, we also went to the femoral artery, which is reaching about 1mm vessel. We checked it by doing a patency test, and that is just milking the vessel distal from the anastomosis, which we use in clinic often, after 15 minutes, leaving the rat alone. And in the end, the rat had to be sacrificed, and we checked the anastomosis by cutting it open. So looking at the aorta anastomosis, it took about 10 sutures per anastomosis in general. All anastomoses were patent. You can have some criticism on the picture. What you can see is that the robot took much longer. Again, in this test too, the hand was pretty quick, in about 20 minutes, and the robot was more than 3 times slower. But it went well. Femoral artery, that was really tryout that we decided halfway the experiment. It took 5 sutures per anastomosis, and there you can see the time of the robot is not that bad anymore. It's about 2.5. We think that's got to do also with the reason that everybody was set up for it, and it went well. The first anastomosis was not patent. There was some leakage, and because of an extra suture, it was not patent. And we had the drawback of the material we used in this robot, as we had normal conventional needle holes. And for the super microsurgery type of operation, when we go there, I think you need nicer material. So in conclusion, looking at the pointing task and the tracing task, you could see the robot is more precise, and in the tracing task is more constant performance in all levels. In the silicone vessels, you could see the hand is still quicker than the experienced microsurgeon, but the learning curve of the robot is steeper. If you look at the time it takes to perform the anastomosis and the indicative scale by the expert panel that was blinded, you could see it's promising. And the pilot study in rats showed an adequate microanastomosis is possible in the aorta, which is about 2 to 3 millimeter vessels that we use in normal microsurgery these days. The time to perform the anastomosis took longer, and that was because of motion scaling and being out of range. And we're getting towards supramicrosurgical anastomosis. The definition is between 0.3 and 0.8, but we were near, and it was possible with our first generation robot we built. So the future, where are we heading to? The lessons we learned from all these experiments, we were able to adapt the robot. So my colleague who is speaking after me from the technical part, he adapted the system so we could overcome the limitations. We are expecting the next robot, and I can't wait, in the beginning of 2016, so it's a few months, and new studies are already planned. But I am a plastic surgeon, so we have studies planned on reconstructive surgery, hand surgery, and lymphedema surgery already. But I think, as we hear today, there is a broad field of robotic microsurgery, so I would invite anybody who is interested in doing research in this field to collaborate and come up to me after the meeting to see, because I think we need to go together. And I also think it's nice to have different systems than only the Da Vinci, with only the Da Vinci score, to set up the next step towards the future. Thank you.